Away.
Okay, so this is joint work with Nicole Eggman, who is my PhD student back at Brunel. And, well, this topic's a little bit different from the focus of the program, but it is a link between combinatorics and physics. It's a different sort of physics, I guess. It's also a bit of a departure for me in that until I started supervising Nicole, I knew absolutely nothing about this subject at all, and now I know just a tiny little bit. So I apologise for any errors in the things that I talk about. So somehow I foolishly agreed to supervise a student in a topic that I knew absolutely nothing about. But anyway, she's a good student, so it's sort of worked okay. Right. So what I'm going to talk about. It's really stuff that started, I suppose, in the 90s when there was a vast amount of papers in the physics literature starting to look at various real-world networks and some of their properties and trying to see what they had in common. And one thing I was thinking as I was writing the talk, that exactly how to say this, but so we've seen in the workshops here over the last few weeks that there's been a lot of very, very good links between combinatorics and physics, and there's often the results that come out of the physics are perhaps not quite as rigorous as we're used to in maths, but they always seem to be right. Whereas in this stuff, the physics isn't, I put it delicately, perhaps quite as uniformly good as that. And there are quite a lot of conjectures and empirical results that are just not right. So I'll start off with some of the empirical stuff just to really set the scene and as a bit of motivation for why people started to think about these things. And then I'll go on to random graphs. I'll say just a little bit about classical sort of random graphs, just so you can see the properties that they have, which show that they're really not the right model for these graphs I'm going to talk about. And then I'll talk about scale-free graphs, which are also not the right model, but in a different way. And then I'll talk about the clustering coefficient and calculating its expectation for one of these models. Okay. So yeah, so as I was saying, there's this huge literature. It's absolutely enormous amount of work on this thing, looking at generally empirical properties of real-world networks. So the favourite one that people like to look at is either the World Wide Web, where by that you mean a directed graph with the vertices as web pages and the edges being hyperlinks. Or you can look at the internet, by which you mean the physical structure making up the World Wide Web. So the vertices are computers or routers or things like that, and edges are wires or whatever you have to join them up. And then you can do all sorts of other things which are more or less serious. So things like mass collaboration network and your Erdos number and all that sort of stuff. Social contacts and even things like electricity power grids, phone calls, movie actors, a bit more fun. And then it gets a little bit stranger. So if you want to look at, if you take all the words in the dictionary and which ones are linked by appearing in the definition of another word, then you get something that also looks like one of these things. And then the other day I was searching for something on the web, and a paper came up that says the scale-free network associated with sheep movements in the UK. So it's obviously all embracing this stuff. So. Okay, so these are the things that people tend to think about. In some cases they're the same things as you think about for any graph, in some cases not. So degree sequence, also very interested in the distribution of distances between pairs of vertices. The diameter, so that's the largest or the biggest shortest path, so the biggest over all pairs of vertices and the length of the shortest path between them. Connectedness, sizes of components. And the thing that I'm going to talk about most, or later on anyway, is the clustering coefficient. And this is 3 times the quotient of the number of triangles and the number of pairs of adjacent edges. So in this graph, you've got 1 triangle and you've got 5 pairs of adjacent edges, because you've got 1 here and 1 here, and you've got 3 ways of choosing a pair of adjacent edges there. So the clustering coefficient of this is 3/5. And the 3 is there so that if you take a complete graph, then your clustering coefficient comes out to be 1. And well, later on the graphs won't necessarily be simple. So you may have multiple edges, and you may have loops, and both endpoints of a loop, both sort of half edges associated with a loop, will count as a pair of adjacent edges. And in that case, you can actually get the clustering coefficient being bigger than 1, but that's a sort of anomaly that's not really very important. Okay, so just focusing on the internet. So these references are a little bit old. I was afraid I was a little bit lazy in looking through the literature. So this is one paper that seems to be referenced quite a lot from about 2000, where they looked at a pretty large subgraph of the internet, although only a very small proportion of it. And one of the key observations is these, I've never used one of these big sticks. Let's see how many go here. This sort of behavior comes up, where you look at the proportion of vertices with a particular degree, and that seems to, the proportion of them seems to scale as some inverse power of d. And in these real world things, it seems to be, the exponent seems to be between 2 and 3. It seems to be something that comes up a lot. Also find the average path length is about 11. And then there were various different papers which seem to get all sorts of slightly different answers for the clustering coefficient. I think that's just because they were perhaps looking at a slightly different criterion for choosing the vertices to go in the graph. Maybe the level of the physical, maybe the level of the components, where they're looking at computers or routers or whatever, gave them different things. And it seems to come out as somewhere between in this range. These guys actually wrote 2 or 3 papers on this, looking at a graph that was selected in more or less the same way each time, and they started off at the earliest time with a clustering coefficient there, 0.18, and over the years it seemed to go up, which is quite interesting for the internet. Okay, so this is a sort of summary of some of the things that people have looked at. So this here is the exponent on the power law giving the degrees. The clustering coefficient seems to go from anywhere in the whole range between 0 and 1, but it does appear to actually be some constant. I mean, here we have a very large graph, and this thing is still 0.1, so if it's tending to 0, it's tending to 0 extremely slowly. And this one here is actually, seems improbably large to me. So that's saying that if you've got any, if you take any actor and look at 2 of their collaborators, the chances are that they will have appeared together, which, in some sense, it's not surprising, because you're going to have a lot of them all appearing in the same film, but even so, it still seems a bit larger than you might expect.
Really that many movies? Must be some C and D movies.
Yeah, maybe it's just, yeah, it's YouTube or YouTube. Something like that. Yeah, yeah. Oh yeah. Yeah. Okay, so I'll just say a little bit about classical random graphs, and then talk about scale-free graphs, just to set the scene a little bit. So GNP, what I guess everyone knows, just a graph, vertex set labelled set, so vertices labelled 1 to n, and we look at each possible edge and we put it in place with probability p, and that's done independently of all the other edges. So these papers here that I've referenced, the Erdos-Renyi papers from 59 to 61, they're the kind of first papers on the random graphs, and much sharper results than these are known. Now, in some sense, for the things I've talked about, it's not clear to me that looking at whether the graph is connected or not is really an important thing, because if you think about, if you think about, say the movie actors thing, or no, let's say the World Wide Web, that if you've got a disconnected bit, that's a sort of group of people who've formed their own network, and they're acting quite differently from everyone else. So they've sort of made some decision that they're not going to connect to anyone else, so they're not really acting in the same way as everyone else. And so it actually seems that the connected components are perhaps not something you should look at. But actually it turns out that these sort of results are not a million miles away from what you'd expect, what you get in real life networks. So we're really in this regime here where every vertex has some constant number of neighbours, and we get a giant component containing a linear proportion of the vertices, and while other component sizes have size order log n, and the graph doesn't become connected until p is about log n over n. Okay, so that's not a million miles away from what we see. On the other hand, the next thing is something that's very different from what actually happens in real world networks. So if you look at the proportion of vertices that have got a particular degree, so xk here is going to be the number of vertices that have degree k, and if you look at the proportion of those vertices in the graph, then asymptotically almost surely, so that means with probability going to 1 as n tends to infinity, this proportion is given, roughly speaking, by the Poisson probabilities. And that's very different from what happens in these real-world networks, where you get this scale-free behavior. Now, if you look at the clustering coefficient, it's sort of stated everywhere that the clustering coefficient of a random graph is obviously p. And providing p is a constant, that's something that you can actually show. It does actually need a little bit of a proof, which nobody ever seems to have written down. It's also stated that this is true, that if I've got the probability of an edge is c over n, so I've got expected degree equal roughly to c, that the clustering coefficient should go to, if you multiply by n, it should go to c. So asymptotically, the expected clustering coefficient is about c over n. And that seems a little more problematical to me. I suspect it's probably true, but I've never actually seen that proved anywhere. So we'll call that folklore. Okay. So then something else, if you take a random regular graph, so GNR here, the sort of abusive notation is going to be a graph where every vertex has got r neighbours, and you sample from them uniformly at random, then you get that the diameter of the graph is about log n over log r minus 1, asymptotically almost surely. And this seems to fit, roughly speaking, with the values I showed a bit earlier on. So some of these properties of classical random graphs fit in with the real-world networks, but some of them don't. So clearly they're not exactly the right thing that you should be looking at. Okay, so I'll go on to another version of a random graph. And this became, or was popularized, I guess, by a paper of Barabashi and Albert, where they defined a preferential attachment process. And actually this model originally goes back to 1925, and there were several papers which have looked at this model, but it had never really caught on until the Barabashi-Albert paper. Now their definition is criticised quite seriously in the Bolobash-Reardon paper, because it's not entirely precise. So what they say, roughly speaking, is that you start with whatever graph you like, and let's say we're going to actually form a tree to begin with. So then what you do is you add a vertex at each time step, and that vertex selects its neighbour by picking a vertex with probability, an existing vertex with probability proportional to its degree. Okay, so there's one kind of trivial problem with that if you start off with just one vertex, you can't actually get started. So so there's numerous ways of getting around this problem. Right, so if you imagine you've just got one vertex to start with, then you're a bit stuck because you haven't got any degree to copy, so you've got some sort of probability 0/0 or something. So there's various things you could do. So you could start off by saying, well, my first graph that I'm going to start with is just going to look like this, and then at each stage I'm going to add a new vertex, and I'm going to copy either this one or this one, so I choose either one with probability 1/2, and at the next step I've got two chances of copying that one of this one and one of this one, so I'll probably copy that one, and so on. So that's one way around it. The way Bolobash and Reardon get around it, well, they have two ways of getting around it. One thing you could do is you could just start off with V1, and you could just add a sort of artificial half edge there, so that vertex always has degree 1 more than it really has, and then you keep going the same way. Second thing you could do is you could start off by saying, well, when I add a vertex, well, the first one, okay, I'll just add a loop to it. But more generally what I do when I bring along the next vertex is, well, I'm going to have an edge coming out of this, and I'm going to count this as a possible, as degree 1 for when I'm thinking of what I'm going to copy. So at this stage I've got probability 2/3 of joining to here, and probability 1/3 of actually copying this endpoint and coming back to here. So with probability 1/3 I'll actually get another loop on there. So a lot of the time it doesn't actually make any difference which model you use, but it makes life a little bit of a pain. So obviously both of these two, the first two I described, are going to be connected, whereas this one won't be connected, because as soon as I choose a vertex which copies itself, then I end up with another connected component. So these two are going to be trees. This one's going to be something roughly like a forest, except that the earliest vertex in each component of the forest will have a loop on it. So I've forgotten which one I've described here actually. This is the right. So this is the one with the loops. Okay. So this is how the Bolobash-Reardon model works. So the first one is just the vertex with the loop, and then we add a vertex and an edge to an earlier vertex, so that you choose it with probability proportional to its degree, and you count your own degree as 1, so you can get a loop. Okay. So all these models are actually going to give us directed graphs, but we're not going to really think about the directions on the edges at all. We can forget about them. Okay, so then we want to get a graph where every vertex has got out degree m. So, well, all you do is just look at this picture. So this is going to be a graph without degree 2. So we run the process on the original thing to get what's more or less a forest. So just think of this as being the m equals 1 case, and then you just merge vertices together. So we just merge all these pairs within the blobs together. And we end up with this graph where every vertex has now got out degree 2 in this case. Okay, so so that's what I've just said there, that we've just merged vertices together. And now you might have parallel edges. Okay, so they proved a result which it's actually quite a hard paper. It's a hard result. So providing m is at least 2, then asymptotically almost surely, so with probability tending to 1, this graph is connected, and the diameter is asymptotically log n over log n. So it's slightly different from what you get for a classical random graph or random regular graph, where we would have log n over log 2m minus 1 in there.
Doesn't depend on m.
No. So I think there was a conjecture that this was, log n in the before they proved this. And then in an earlier paper they were able to obtain the degree, or the number of vertices with a particular degree, where this degree is small, but this covers pretty much all the vertices in the graph. There are very, very few vertices that have a degree bigger than that. So they show that the proportion of vertices of degree d is, roughly speaking, this constant alpha md, where alpha md is about constant over d cubed. So this is an exponent of 3 in those things that we saw earlier on. Okay, so one way which you could generalize this is to say, well, go back to the tree, let's say, so when I'm going to pick which vertex a new vertex is going to be joined to, rather than just looking at the degree of that vertex, I could add on some constant. And this is something that's called sort of inherent attractiveness of a vertex, and there's been quite a lot of empirical work done where this takes different values for different vertices. But it gets to actually analyze this carefully makes things get rather complicated. So Buckley and Ostus have shown that a result that's really similar to the Bolobash-Reardon result, but I haven't really got room to write down all the formulae. It gets a little bit complicated, but essentially they show that the number of proportion of vertices with degree d is proportional to d to the minus 3 plus a. So this is where a is any positive integer. Now, this is starting to get to something a bit unlike the real world things, because in the real world things this exponent in here is always between 2 and 3, so it's moving in the wrong direction. But this model, the Mori model, will actually have a possibility of going in the right way. Now, so this is more or less the same as the previous one, except that this beta now is any positive, strictly positive real number. You can also do this in Mori's paper. He also goes down to beta strictly greater than minus 1, but I'm only going to work with it later for a reason that will become clear in the next slide, for beta greater than 0. Okay, so it's more or less the same as the previous model. We just start with 2 vertices joined by a single edge, and at each stage we add a new vertex, and the new vertex is going to join to something with probability proportional to the degree plus this constant beta, and this thing on the bottom is just the right thing to make all the probabilities add up to 1. So this will give us a tree in which every vertex except the first has got out degree 1. And then when we want to form the thing with out degree m, we do exactly the same trick as before, merge the vertices, and you may get loops and parallel edges, and you can throw them away if you want to or not, but you don't get very many of them, so they're not something that you really want to worry about too much. Okay, so there's another way of thinking about this, which is to be quite useful. So if we think of this probability, we can rewrite it as some linear combination of this and this. And this says, so if we're adding a vertex at time t plus 1, so there are t vertices and hence t minus 1 edges already present in the graph. So we've got 2t minus 2 endpoints already present. So you either pick a random endpoint of an edge and join to where that endpoint joins to, or with some other probability, you pick a random vertex and just join to that random vertex. And you need beta to be bigger than naught, otherwise this number in here is negative. Okay. So this is another way of thinking about this, that you've got either this copying an endpoint, which we'll call preferential attachment, or copying a vertex, which we'll call uniform attachment. Okay, and one result for this graph is that the maximum degree is quite well understood. And essentially what Mori proves, he proves a number of results concerning the convergence of something that's a little bit like the maximum degree, so delta n is going to be the maximum degree at time n, divided by n to the 1 over 2 plus beta. And essentially what he shows is that this thing here converges to a random variable that's extremely well behaved, that's non-zero almost surely and has all its moments exist. So one thing to say about this is that if you extrapolated the power law that you ought to get for this graph, so we should get the proportion of vertices with degree d being n to the minus 3 plus beta. So if you extrapolated that to where you'd expect to only have one vertex with a particular degree, so until that function goes to 1 over n, then doesn't come out as n to the 1 over 2 plus beta. It's not the same thing. So the maximum degree isn't what would be predicted by the power law. So the power law certainly goes wrong as you get up to the maximum degree. Okay, so so now I've gone to the clustering coefficient and how we found that. So I think this thing was first introduced by Watts and Strogatz. So this is the paper where they coined the small worlds term, and they described a small worlds network as something where it's got constant clustering coefficient and the diameter is logarithmic. And they defined a local clustering coefficient, so it's just the number of triangles involving vertex v divided by the number of edges coming from v, choose 2. So it's the probability that two neighbours of v are joined by an edge. And then there's various different ways of defining a global clustering coefficient. So you could either just take the average of all the local clustering coefficients, or you could take a sort of weighted average where you weight by the degree of the vertices, choose 2, which conveniently enough gives you quite a nice formulation for the clustering coefficient as 3 times the number of triangles divided by the sum of the degrees, choose 2. This one is sort of probably not the right thing to take, because most of the vertices in one of these scale-free graphs have got a very, very small degree, and so they're going to have, somehow it seems like they're having much too big an effect on this global clustering coefficient if you just take the average. And also this thing is a bit easier to analyse, also it turns out.
Do we have a 3 missing parts?
No, because No, because in here I will have summed over each triangle 3 times. Okay, so what we can show is that providing beta is bigger than 0 in this model, that the clustering coefficient asymptotically is log n over n, which in some ways is a bit unfortunate because it means that these graphs are not small worlds networks. And we know what this constant is, it's just not terribly informative. But you'll see what it is if you look at some of the expressions that come up. Okay, so I'm going to talk a little bit about how we prove this. And this proof is more or less based on, so I'll tell you in a moment that Bolobash and Reardon had a different result for when beta equals 0. And the proof is more or less based on their approach. So we find, first of all, an expression for the probability that the tree contains some fixed labeled subgraph. And then we can use this to find the expected number of triangles and the expected number of, the sum of the expectation of the sum of the degrees choose 2. So then we want the expectation of the quotient. So we then do what all my students would do, which is just to divide the expectation of the top by the expectation of the bottom. But we're going to justify that by proving a concentration result, saying that this is tightly concentrated around its expectation, and my students tend not to bother with that bit. Okay. Right, so I need a tiny bit of notation for this. So we're going to, first of all, just define a feasible forest. So a feasible forest is just something which can occur as a subgraph of one of these growing trees. And it's kind of handy, even though we're only thinking about them as undirected graphs. Thinking about them as directed graphs is just kind of handy for notational purposes and for writing down the formulae. So V minus is just going to be things with in degree, positive in degree, and V plus is just going to be things with positive out degree in this labelled subgraph that we're going to think about. So yeah, sorry, that's something I should have stressed. It's a labelled subgraph I'm going to think about. I'm going to think of a subgraph on a particular set of vertices, and the probability can find that in the graph. So if S here is my labelled subgraph, so so V minus is red and V plus is blue, and that one's purple because it's in both. And CS, so this is just going to be the number of edges from a particular point onwards to an earlier set. So I think CS of 4 is the green edges in here, because they're from 4 or something later to something earlier than 4. Okay, so Bolobash and Reardon had an expression for this. This isn't quite their lemma, because there's a slight variation in exactly which of these models, as I talked about earlier on, using here. So this is, I've changed their formula to cope with that, and it's actually not quite as nice in this case. So it's essentially, as you can see here, it's just a product over the vertices that are in V minus and V plus, and some extra stuff on the end here which will turn out to be small and we can forget about. And then for general beta, this is not too difficult to generalize this to this. It really is just a matter of putting gamma functions wherever you see a factorial in here and putting the right thing on the bottom here. So if beta equals 0, you get that. So it's exactly the same proof to do what they did, but it's a nastier formula.
And it's going to come out in 2010?
Well, you know. It's an estimate. It's on the archive already. And okay, so a slightly more useful thing to do is to write it like this. So we get some term which is for every vertex in V minus, and then for every edge, the key thing is this term here, which is so the larger vertex, the 1 plus beta over 2 plus beta, and the smaller vertex, 1 over 2 plus beta. And this term here we're going to show that this term here is actually quite small, because so this is just going to be, if we've got a small subgraph, this is just something to do with the number of edges in the subgraph, and this is going to get quite large as the labels on the, it's going to, well, we're going to bound this term by 1 plus 1 over n, 1 plus o of 1 over n, so this is going to be small. Okay, so then what you do is you work out, want to work out the probability a particular triangle is in the graph now, the M out graph. So you just have to think about what a triangle is going to look like in that graph. And there are actually two cases. So if you think of this as, so this is probably the case m equals 3, let's say. So this is vertex A. Vertex A in the merge graph, so it's AM in the tree, BM and CM. So a triangle could look something like this. There are two cases, because you could have this vertex being hit twice in a triangle, and if you plug that into the formula from the previous page, you get previous slide, you get an expression which looks a bit like this, and you can easily count how many there are of these triangles, and then you can sum over all A, B and C and get the right number. And the alternative, oh, that's a funny triangle, it's only got 2 edges. Not sure what's happened there. So there should be another vertex here which has somehow got deleted, joining back to something over here. And you get something slightly different because you've got 2 vertices here within degree 1. So you have to do through all the various cases. And if you do that, something slightly odd happens, because in the case when beta equals 0, when you do the calculation, you get log n cubed, essentially, plus smaller order terms, whereas when beta is greater than 0, you get log n plus constant. But obviously something very strange is happening when beta goes to 0, because this expression isn't well behaved. But I don't really know why this works. It just seems to be something that comes out of the calculations, because you do, to work these things out, you do various integrals, and when beta equals 0, you have a lot of integrals that are sort of 1 over x, so you get lots of logs coming out, whereas here that doesn't happen. Okay, so then if you do the same sort of thing to work out the number of pairs of adjacent edges, you get n log n for the case when beta equals 0, and in the more general case, you get beta is greater than 0, you get order n plus some error term. And well, for instance, these things aren't actually particularly surprising, because so if you take this one here, so this is saying we've got a graph that looks like this. Well, every vertex in here has got m out neighbours, and most of the time all of those m out neighbours will be different, and then most of the time all of the out neighbours will have m distinct out neighbours, so you really have got m squared n paths of this form. And you can have a similar argument with this one to show that this isn't particularly surprising. I don't think you can see this one without actually doing the calculation. And you can check, there's various sort of degenerate pairs of adjacent edges. So this is a vertex that's got a pair of adjacent edges. You can show you only get log n of those, constant number of things like that, log n pairs of parallel edges. But you get quite a few things where you count one of these edges and one thing from the loop. Okay, so far we've got the expectation of the bottom of this thing and the expectation of the top, and we now want to take the quotient of those expectations and say it's the expectation of the quotient. So to do that, we need a concentration result, and this is actually the most interesting part of the whole thing. So we can essentially show this, that the probability that the sum of the degrees choose 2 minus its expectation is bigger than n to this particular power for any epsilon greater than 0 goes to 0. And this is just enough because the exponents, this thing is just a tiny bit less than 1, and we've got that this expectation is about n log n, so this is just enough to show that it is tightly concentrated around there. And this we prove using martingales and so on, and so I'll go through some of that. So this was completely new to me, how to actually apply these things, so we'll go through some of that. Okay, so needs a little bit of notation, but it's actually not too complicated. So what we've got is we've got x1 to xn are going to be some random variables that essentially define how our process is working. So they can be, you can think of these as random variables that are telling you exactly what happens in the graph as you build it at each step. So whether you preferentially or uniformly attach, and which vertex you attach to. And f is going to be some function of those, so f is going to be our sum of the degrees choose 2. So what we're interested in is this function g, which is really just a function of what happens at time s. So imagine that we're given the evolution of the graph up to time s minus 1, and this g is going to tell us what the expectation is if we choose x. So if something precisely happens at time s, what the expectation of this sum of the degrees choose 2 is going to be, given what's already happened. The next thing we need is this thing ran, which is range, which is going to be the biggest difference that can happen to this expectation of the sum of the degrees choose 2 by something different happening at time s. So by choosing a different vertex to attach to. And then the thing we need to do is to find the sum of these. So if we take a particular way in which the graph might evolve, we need to work out this range of x2 up to xk minus 1 and square it and sum it. And this is essentially going to give us, when we take the supremum of all possible values of this r squared, this is going to essentially be the maximum sort of variation that we can have in the process. Except we're allowed to cheat a little bit. We only have to maximize over certain possible ways that the graph may evolve. We're allowed to exclude certain bad ones, which will be some bad subset B. And then the probability that f differs from its expectation by more than some t is just given by this exponential, plus the probability that x, so the way the graph evolves, lies in this bad set. So the key thing to do is to show that we can bound this term here. So this is the expectation of the sum of the degrees choose 2 if we're given the graph up to a certain time, but then different things happen at a particular time step. And I'm not absolutely sure who this theorem is due to. So if you don't have this b in here, and you make various other assumptions about x1 to xn, then it's an old result which is sometimes attributed to Azuma and sometimes to Azuma-Höfting. But I don't know whether this is, people in the audience may know this, whether Colin is actually responsible for this result. It appears in his book where he surveys these things, and he doesn't attribute it to anybody else. So that's my small amount of evidence for putting his name there. Okay, so this is the basic idea of what we're going to do. So imagine just in the tree we've got two vertices vi, vj, and we're now at time t, and I've given you the evolution of the graph up to time t minus 1. We're going to compare what happens with two different things happening at time t. So at time t, either I'm going to attach to this vertex, or I'm going to attach to this vertex. I'm going to consider the difference in what may happen to the sum of the degrees, choose 2. So the way to do this is to essentially build up, well, a partition of all the edges that are attached to these vertices as we go through later times from time t. And we're going to have one block of the partition is going to correspond to each of the edges that are there already. So this is the special one which was kind of moved from here to here when we did different things at time t. And this is a special one that's originally empty, initially empty, which I'll mention later on. So what we do is the graph builds up. If I choose at the next stage, say, to preferentially copy this edge, I throw this endpoint of the edge into that block there. And let's say that at the next time step I chose to uniformly copy this vertex. So then I'm going to throw it into this green, special green thing. And say at the next stage, well, I've thrown something into here. That could be for two reasons. It could be because I've uniformly copied again, or it could be because I've preferentially copied an edge that's in there. So what I do at every stage is, if I preferentially copy one of these endpoints, I throw the edge into the block containing that particular endpoint. If I do something uniformly, I just throw it into the green one. Okay, so then next stage, I might have preferentially copied either of the two things that are in there. So let's say at the end I end up with something like this at time n, the time that I'm actually interested in. Well, so the distribution of the number of endpoints in each of these blocks, well, for all the ones apart from the green ones, these are all have the same distribution. And the two green ones also have the same distribution. So if I want to work out what the difference in the expectation of the sum of the squares, the sum of the degrees choose 2, and these two different situations are, well, if I think about what would have happened to the graph had I not moved this edge, if it had continued evolving in the same way, we'd just have all these edges would now be attached to this vertex. So everything else would have happened in exactly the same way. And so that makes it quite simple to work out what the expectation is, the expected difference in the sum of the degrees choose 2. All I've got to do is I've got to work out what the expectation of the size of one of these things times the size of one of the other things is, and multiply it by the number of the difference in the degrees at time t. So that's what I just said. I just got to, if x is, say, the size of one of these things and x dashed is one of the other things, then the difference in the degrees choose 2 is just the expectation of this product times the number of the difference in the degrees at time t. So that's just the number of blocks, the difference in the number of blocks. Okay, and this thing we can bound by the maximum degree at time t. And we saw earlier on that the maximum degree at time t was quite well behaved. So, well, I won't go through all the details, but so yeah, so the RAN thing, which is the maximum degree times the size of that expectation. So that expectation turns out to be roughly this, which is quite easy to that's quite easy to compute. And then if you let the bad set be evolutions of the graph where the sum of the maximum degree normalized is getting big, then you can show that r squared, which is just this sum, comes out to be this. And so the probability, if you go back to the original theorem, is just going to, that you're bigger than this, is just, so it's just this divided by so it's this squared divided by this, which gives us that term, plus the probability we're in the bad set. And Murray's result on the maximum degree shows us the probability that the maximum degree evolves like this is very small, and so this tends to 0 quickly enough for us to be able to prove what we want. Okay, so that's this stage of the proof is actually quite straightforward. It's just kind of not something I can really explain very easily right now. Okay, so just a summary to finish off. So we showed that the expectation is log n over n. So this means there's some sort of phase transition at beta equals 0. Something funny happens there. I don't really know why. So beta equals 0, the answer would be log n squared over n. I don't really understand why that happens. And unfortunately, this means that the Mori model, or the BA model, Barabasi-Albert model, doesn't display one of the key properties of web graphs, doesn't display the small world property. The small world property would mean that this thing should be tending to a constant. And the other thing I don't know is we've only really talked about the expectation of the clustering coefficient. I don't know whether the clustering coefficient itself is tightly concentrated around its value. So I don't know whether the methods we've used could be generalized to do this. It seems quite a bit harder. I don't know how to do it at the moment. Okay, so I'll stop there. Questions?
Is the diameter controllable?
In what sense?
Can you get bounds on the diameter for these things?
Well, you can for the beta equals 0 case, yeah.
Oh, for beta positive.
I'm not sure. I haven't thought about it. No, I'm afraid I don't really have any intuition on how that would work or not. I think I'm not sure it's even done for the kind of pure uniform attachment case. So whenever you add a new vertex, it picks its neighbour uniformly. I don't think it's done for that. The Bolabash-Reardon paper doing it for beta equals 0 is really quite tough going, so I wouldn't fancy generalising that.
Standard sort of daft laddie question to ask whenever you get a phase transition like this is to observe that usually these things, if you look at them from a different angle, you can smooth them out a bit. Do you have any sort of conjectural idea even about some kind of modification of the structure? I mean, for example, you could have that whenever a new vertex comes along, it tosses a coin, and if it's in a certain route, it does take account of the inherent attractiveness, and if it's in another route, it doesn't. And could you maybe get regimes between log n over n and log squared n over n by playing around that way?
I suspect that you'd still get log n, log squared n over n for that one. Sorry, log n over n for that one. I suspect that doesn't make much difference compared with the model we've got.
There might be some other way of...
Yeah, I haven't... this was actually conjectured to be... so there are people who... Some of the papers written on this are a bit obsessive with coming up with power laws and things, and this was... Clustering coefficient was conjectured to be n to the minus 3/4, or something like that. Which, yeah, it's not.
Is there any particular reason that the clustering coefficient is defined to be essentially the number of triangles divided by this thing? Because one can imagine that, cycles of length 4 might be important if there are no cycles of length 3.
Right. I think it's just that, yeah, sure. I'm sure you could define something like that. I think the thing is just in these graphs there are a lot of triangles, and so it then becomes a natural thing to do. And it's kind of interesting in the random graph because you're almost thinking about so I give you a random kind of V or pair of adjacent edges, and I ask you for the probability that third edge is there, but it's not quite that, because if the third edge was there, I'm a bit less likely to have given you that particular V. So it's actually quite subtle what's going on in some places. It's quite an interesting thing to play around with.
Is there another model which may have more of the properties of web graphs?
There are all sorts of models, but I don't have another nice model. Because you can just, if you're not careful, you end up copying exactly the graph you started with. And so there's some geometric things where you copy vertices only if they're reasonably close to you. You throw points down in the plane and you copy vertices that are close to you, and
By copy you mean join?
you join to things, that are close to you. Perhaps with probabilities also depending on the degrees and so on. There's a paper by Alan Fries on that.
Start with an arbitrary graph and then just run your preferential attachment.
Mm-hmm.
You get the same thing no matter what you start with?
Not necessarily, no. I think the degree sequence will turn out to be what you expect. So in Bolobash and Reardon's paper where they do the clustering coefficient, so one of their criticisms of the Barabashi-Albert model is that Barabashi-Albert say you can start off with whatever you like, and I think they show that you can actually get different clustering coefficients depending on what you start with. But yeah, it's a while since I read that, so I'm not 100% sure.
Line to get you away from the pub last night.
Oh, the last.
That one?
No. This one.
Ah, okay.
Yeah.
Yeah, I can see that.
Yeah, that's the way they're doing. Yeah.
Many pictures.
Yeah. Okay. So, anything else?